Hi there. This is the final topic in Fundamentals of Surveying. Here I'll discuss to you Earthworks. Earthworks is a generic term for all items of work, materials, and operations required to construct excavated areas and the embankments of a project. So it is necessary for us to study earthwork because in any construction project, excavation and embankment of soil is always involved. In general, earthwork on a highway project consists of embankment, compacted fill material needed to construct the roadway, excluding the base and pavement portions of the roadway and shoulders, regular excavation or the excavation necessary for the construction of the roadway, ditches, ponds, channel changes, and subsoil excavation. Excavation, removal, and disposal of any material that is unsuitable on, on its original position, and that is excavated below the finished grading template. So here in this lesson, we will just focus on embankment and excavation soil. So embankment is the compacted fill material needed to construct the roadway. So if we have here a cross section of roadway, so that area there that we will be needed to compute the embankment, the volume of soil needed is this portion here, because if this is your existing ground surface, okay, or the original ground line, okay, and we have a finished grading template, or the roadway that is being proposed is at this elevation, so it is not safe if we just construct a road there without putting an embankment at the left side of the cross section. So for it to be safe, we should have an embankment here, and depending on the specifications in our country, that is allowed for the slope needed here on this side, we shall follow that. But usually we have a horizontal of 1.5 is to 1 vertical. So this portion here is the embankment. So for the cross section, the area here is called the fill. So the term we use for that area needed in computing the embankment is the fill. On the other hand, for the excavation, so the volume of soil needed to be removed on the existing ground surface, existing ground line, which is this one. Since in this provision of this cross section, they we put drainage. So depending on the required, if drainage is required on the cross section on the roadway that is being designed, so we put drainage such as line canal or earth canal. So in this example, this is an example of earth canal, where we just excavate some portion on the right side of the roadway, so that when it rains, the runoff of rainfall goes to the sides, and this area here will serve as drainage for the roadway, so that the water will not stay in the middle of the roadway. So this area here that is needed in calculating the volume for embankment is what you call the cut. So this is cut here. So in fundamentals of surveying, we'll just focus on embankment and excavation. So usually in roadway design, there is a separate computation for subgrade preparation. But here we'll just study on the fundamentals. So here's a sample cross-section of a roadway. So in actual design of roadway, uh, we make this and we compute the area of fill, area of cut on the cross section. And we also record there the additional items needed because these are essential in computing the cost in the project. So especially in earthworks, uh, earthworks are always computed in terms of the volume. Okay, so if we are in metric, how many cubic meters of soil of for embankment, and how many soils are needed for excavation. So that's how the cost for earthworks are computed. That's why it's necessary for us to first determine the area of cut and fill before computing the volume of soil. So here in this cross section, this is an example for excavation where we need to determine first the area of the soil needed to be excavated. So right here, this is your road, okay, and this dashed line here is the existing ground surface. So the area needed to be excavated is right here. So if the design involves line canal, so this portion also should be excavated. Okay, so that should be excavated. On the other hand, for embankment, the if the proposed roadway has an elevation higher than the existing ground surface, okay, we need to fill that area, okay, from the ground surface to attain the desired elevation of the roadway. So we need to determine the fill, the area of fill, and if there is cut, if we have here drainage or earth canal, so we excavate that area. So if if the slope is too high, we can put there, can design there some riprap, uh, stone masonry structure. So we just record there on that. So for the area of cross section, we have two solutions that we can use. First one is area by trapezoidal rule and the area by Simpson's one-third rule. So the area of any irregular plane figure, such as this one, can be found approximately by dividing it into a number of strips or panels by a series of equidistant parallel chords. So we have here strips here, equidistant strips. Okay, dividing that with the same distance, and through that we compute the total area by first determining the heights at each point. Okay, so h1, h2, h3, h4, so on. So we determine the distance, determine the height at each strip, and using these two formula, we can compute the cross-sectional area. So for trapezoidal rule, the solution is this one: d over 2, quantity of h1 plus 2, quantity of h2 plus h3, and so on. All the heights between the first and last station or point, all of these values here, plus h of n for the last station. So we multiply that to d over 2, or the distance here between two stations divided by 2. So this formula is just derived on assuming that each strip is a trapezoid. So this is a trapezoid here. Okay. So we ignore that curve here, curve line here, this portion. So we simply ignore that and assume that this is a trapezoid. So that formula is just derived from computing the area here, the area here. So at area at each strip. Okay. So if the stationing is too many, so it's not necessary for us to manually compute the area at each strip, each trapezoid, but we just simply use this formula, which is easier to memorize. D over 2 accounted by h1 plus 2 times the sum of all the heights, intermediate heights, then add h of n, or the last station, height of last station. Area by Simpson's rule is that we use this formula, d over 3, quantity of h1 plus 2h, add plus 4, the sum of heights, even, plus h of n. So it is required here that the number of station should be odd. Okay, so here h1 is the height at the first station, h of n is the height at the last station. So here 2 times the sum of h odd, or h odd is the sum of all the height at odd number stations. So if it's 1, 2, 3, so 4 and 5. So you add the 2 for a sum of odd numbers. So for the sum of h even, so sum of heights at even stations. So here 2, 4, and 6. Okay, so this is for heights of even. Okay, so n should be odd. Okay, because this formula is uh, somewhat derived from Prismoidal formula, which means in Prismoidal formula, it requires three stations. We need the midpoint, the first, and the last. Okay, which means we need uh, three stations, which is an odd number of stations. So if we continue computing the areas of that, it always require midpoint or mid station between two stations. So uh, this last station here is 5. So and so on. So if there are many stations, um, our needed number of stations should be odd number. So what happens if the last station is an even number? So this is h of a. So what will happen to our solution in computing the constitutional angle using Simpson's one-third rule? So what will happen is we compute the area from station 1 to 7 using Simpson's one-third rule. And the remaining station, we just simply compute it by trapezoidal rule, or the area of the trapezoid of the remaining state, or the remaining area between station 7 and station 8. So that we can compute the total area. Okay. For example, connection with a construction project. It is desired to determine the difference in area between the edge of a straight road and an irregular riverbank by using trapezoidal rule and Simpson's one-third rule. The following perpendicular offsets were taken at the corresponding stations. So This is one of the applications of using the trapezoidal rule and Simpson's one-third rule is in hydrographic survey. We compute the cross-sectional area of a riverbank. Okay, so here's the data. Given are the offsets from road edge, and these are stations. So what we mean by the offsets here are the depth of the riverbank at each station. Okay, because it is said there that these are perpendicular offsets. So let's say this is the road, this is your roadway, and here is your riverbank. So say this at station 000. Okay, let's say yes, this is station 00. Okay, we had the depth, we have a depth of 10.35. Then station 020, we have this depth here, which is 11.46, and so on. So let's draw the cross section properly on the next slide. Okay, so here are the heights at each station. So we draw that series of strips. Okay, we assume that it is trapezoid. But if we use Simpsons, we can draw it as curved surface here. Okay, but let's say this is trapezoid because the first solution that is needed is by trapezoidal rule. So using trapezoidal rule, we just simply apply the formula. Okay, so using trapezoidal rule, the area is equals to d over 2 times the quantity of h1 plus 2 times of the heights, intermediate heights, h2 to h5. So h2, h3, h4, h5, and the last station is h6. So area 1 is equals to 20 because distance between two stations 0, 0, 20, so they are all equidistant from between stations. So we have a distance of 20, 20 over 2 times 10.35 plus 2 times 11.46 plus 6.30 plus 8.20 plus 15.65 plus 12.22. Okay, computing all that, we have 1057.9 square meters. Okay, that's your cross section area. Okay, how about Simpson's one-third rule? So for using Simpson's one-third, say area 2, the formula is d over 3 times h1 plus 2, the sum of h odd plus 4, the sum of h even plus h of n. Okay, so as we can see here, how many stations? We got 6 stations. So this is an even number of stations. So uh, the Simpson's one-third rule is applicable from station 1 to station 5 only. Okay, because station 5 is an odd number station. So we apply Simpson's one-third rule from station 1 to station 5, and we use trapezoidal rule from station 5 to station 6. So let's rewrite the solution here for the area 2, T over 3, h of 1 plus 2h3 plus 4 h2 plus h4, and we end at h5. The remaining, we have d over 2 times trapezoidal rule, we have h5 plus h6. So h6. Okay, so 20 over 3 is the quantity of 10.35 plus 2, 6.3, sorry, plus 4 times 11.46 plus 8.2 plus 15.65. Okay, plus 20 over 2 times h5 is 15.65 and 12.22. Okay, 2. When we compute all that in our calculators, we have an answer of 1060.30 square meter. Okay, so at least when we compare the two answers, we have almost similar answer. 1057.9 is very near in the area using Simpson's one-third rule, which is 1060.3 square. So when you compare, the answer uh, should be almost similar. Okay, so that's how you solve cross-sectional area using trapezoidal rule and Simpson's rule. Next, so now let's solve some problem in determining the area of a cross-section of a roadway. So it is given here that we have a width of 12 meters. Given here is the cross-section notes. Okay, cross-section notes of the roadway. So how do we draw this cross-sectional notes? So as you can see here, we have values on the upper value without a sign. On the lower values here, we have positive signs. So, so here at the bottom part, which is numbers with positive signs, this is an indication that these values are the height, or this could be the difference in elevation between the roadway and the existing ground surface. Okay, how about on the upper row? So these values are what you call the offsets, horizontal offset from the center line of the roadway. So say this is the center line of your roadway. So these offsets are measured from the center of the roadway. So as you can see here, at the center we have a value 0. But in some cross-section notes, uh, this 0 here is not written. It's directly written here, the the height at the center. So putting the putting number at the center without the offset means that that's the center point of the cross section. So again, we have a center line, and it is given there that we have a road width of 12 meters. So of course we use two-lane roadway, which means that 12-meter row should be divided equally at each lane. which is 6 meters each. So at the center, we have a positive 2.8. So that positive 2.8 means that if we have a positive value for the height, it means that we are going to excavate, or we have a cut here, because uh, this elevation here, or this difference in elevation here, means that the ground surface is 2.8 meters above the roadway. So that's from the roadway, we have positive or plus 2.8 meters, and that's the point where your uh, ground surface is. So here on the right, we have 11.2 offset. So from the center line, we measure 11.2. Then from the road elevation, we measure the difference in elevation of positive 4.2. So we measure vertical plus 4.21. Okay. So if this is the edge of your roadway, it means that point right there is the side slope. Okay, from the edge going to the point where we locate this point right here, which is 11.2 and positive 4.21. So the line that will be drawn between these 2 points is your side slope. Okay, so we can verify also what is the side slope of this by simply subtracting the 11.2 by 6, which is 5. I think that's 1.5 to 1 also. On the left side, uh, we draw 9.8 and positive 3.2. So measure horizontally from the center line 9.8, and we have 3.2, slightly higher. So that's your point right here, 3.2. Then connect it to the edge. That's your side slope. Then connect the 3 points. Okay, connect the 3 points, and that's your cross section of the road. Means that this area here, point here, is the area that should be excavated, or the area of the cut. So if your values here are negative, means you are going to fit. Okay, so let's find the area of this. Okay, so I just redraw the figure. So let's compute the cross-sectional area. So 9.8 minus 6, this distance here is about 3.8. Okay, so how do we compute the cross-sectional area of the roadway using the cross-sectional notes? So what we will do here is, the easiest way to compute the area is we divide it into several triangles by connecting that point here to the midpoint of the roadway, then another here, connect that to that corner there, and as we connect it here, we form several triangles. This one, two, three, and four. So we have 4 areas. So don't do the area. The total area should be the sum of area 1, area 2, area 3, area 4. So for area 1, so we'll just apply for the area of triangle is 1/2 base times height. Okay, so 1/2 base times height. So here for the area total, 1/2. So for area 1, the one that will serve as base here is this one, 6. And height, altitude, the perpendicular distance from the base to the highest point. So that's 3.2. So that's your height. 3.2 plus 1 half. For the second triangle, the base is right here. This distance here is 2.8 times the height. Your height will be 9.8 plus 1 half. For the third triangle, your base is 2.8 and the distance that will serve as height is from this base going to this point, which is 11.2. Okay, plus 1 half. Your base here is 6 and the perpendicular distance going to the vertex is 4.21. Okay, so the total area is equals to, compute that, we have answer of 51.63. So I think we are in meters, so we have area of 51.63 square meters. That's your answer. Now it's time to compute the volume of earthworks. So especially in cross-section of a roadway, uh, we have two solutions again. First one is the end area method, where we just simply take the average of the area of the two stations and multiply it to the distance between the two stations. Let's say we have station 1 and station 2. Just determine the area of station 1 and 2 and take the average of that and multiply it by the distance z. Second formula is by prismoidal. So as we recall this formula, this is the prismoidal formula which requires three areas. Okay, so we have here area median. So L over 6 times the quantity of A1 plus 4AM plus 8. Okay. So since end area method, when we could use end area method, uh, there should be correction because um, the prismoidal formula is the more accurate solution determining the volume of earthwork. However, in the end area method, we can still compute the correct volume by applying the correction, which is called the prismoidal correction. So the prismoidal correction formula is L over 12 times the quantity of C1 minus C2 times the quantity of D1 minus D2. C1 and C2 is just the vertical distances from the center line, okay, from the midpoint of the roadway to the existing ground surface. Okay, C1 and C2, and D1 and D2 are the total horizontal distance of the cross section of the roadway. Okay, D1 and D2. For the corrected volume, just subtract the calculated volume for the prismoidal correction to the volume computed in the end area method. So just subtract the computed end area method by the calculated prismoidal correction volume. Okay, sample problem. Given the cross-section of proposed municipal road, determine the volume of earthworks by end area method, and letter B, the corrected volume using prismoidal correction. So we have here two stations with given cross-section nodes. So let's draw the cross sections. Okay, let's start first at station 1 plus 100. This is the data. So it is not mentioned there, the problem that we have given width of roadway. So that is still unknown. So we put here b over 2 for total width of b. Don't have yet, but we can draw the other points. Can still draw the cross section here without the width. So we have 1.5 at the middle, which means that it's the height at midpoint. Okay, height of the existing ground to the proposed or the finished roadway. So if this is the roadway here, 1.5 above it, that's the point where your existing ground is located. Okay, on the sides, uh, we have 4.5 and positive 1. So let's say 4.5 horizontally is about right here, and positive 1 is a bit lower here. So let's say this is your side slope here, because I assume that this point here is positive 1 and 4.5 from the, that's 4.5 from the center. Okay, on the left side we have 6.45 and 2.3. So 6.45, let's say 6.45 is right here, and 2.3 slightly above the midpoint elevation, let's say this one. Okay, then let's draw a line that point, and we put dimensions of positive 2.3 and, sorry, it's 2.3, and total horizontal distance or offset from the center line of 6.45. Okay, so connect and connect here. So that's your cross section. Okay, so for that, we can compute the base. Okay, how can we compute the base? If we don't have a given road width. Okay, so in designing the roadway, it is always the side slope of the cross section of roadway should be uniform, of the same slope. So it means that the slope here at any stations are always the same, which means the side slope for the next station, station 1 plus 120, is also the same as the slope at station 1 plus 100. Also, the slope on the left side and on the right side of the cross section is also the same. So that's why, from that principle where the slope is equals to rise over run, or the vertical distance over the horizontal distance of that slope, um, we can just simply make an equation in order for us to determine the width of the roadway. So if we have 6.45 total horizontal distance from the center line on this left hand side, or on the left side slope, so let's determine the horizontal distance here. So that horizontal distance is just 6.45 to be subtracted by the b over 2. So that will be 6.45 minus b over 2. Then on the right side, that 4.5 there, just subtract b over 2 to determine this horizontal distance of this slope right here. So we will make an equation by just simply equating the slopes. Okay, let's just equate the slope at the left side, left, to the slope on the right. Okay, apply this rise over right. Rise is 2.3 on the left divided by run, or the horizontal distance 6.45. This one, horizontal distance minus b over 2 equals to rise of 1 over 4.5 minus b over 2. Okay, cross multiply. 2.3 times 4.5 minus b over 2 equals to 6.45 times 1 and minus b over 2 times 1. Okay, distributive property, we have 10.35 minus 1.15 b equals to 6.45 minus b over 2, or b over 2 is 0.5 b, negative 1.15. So we combine like terms. So if this is 0.5b, we transpose that on the left hand side. We have plus 0.5b equals to 6.45 plus 1 point, uh, sorry, 10 point minus 10.35 minus 10.35. Okay, we have negative 0.65b equals to negative 3.9. Divide both sides by negative 0.65. We have an answer of 6 meters. Okay, positive 6 meters. It means that your B here is 6 meters. So we distribute that on each lane. Means that we have 3 meters here, 3 meters on the right lane. So by redrawing figure, that's your cross section here for station 1 plus 100. So station 1 plus 120, since we already have the road width, so we can just simply copy the road width of 3 meters at each lane, then apply this cross section to draw the figure. So if we're going to draw the figure of this station 1 plus 120 with center height of 1.2, offset 6.9 on the right, height of positive 2.6, and on the left side 6 meters, offset positive 2 height. This would be the equivalent drawing for station 1 plus 120. Okay, so let's now determine the area. We can determine the area by computing or by dividing it into 4 parts. So you divide it into 4 parts and determine the area of each triangle. Okay, so for area 1, or area of the first cross section, so area 1 plus area 2, area 3, area 4. Area 1 is triangle here, 1 half base times height. The base is 3, so 3, height is 2.3. For area 2, the base here is 1.5 times the height. This one is the height for this triangle. The height is 6.45. Plus 1 half. Base is 1.5. The height is 4.5. And for the area 4, area of the fourth triangle, base of 3 and the height of 1. Okay, area 1. Now this area 1, when you compute, you have 13.1625. It's 1625 square meter. So station 1 plus 120, same procedure, divided into 4 area. So for area 2, area 1 again, area 2, area 3, area 4, and depth. So area 1, 1 half base, 3 height, 2 second triangle, base 1.20, and height is 6. Yes, 6, and third 1 half, 1.2, and height of 6.9. Last triangle, 1 half, base is 3, height is 2.6. So with the total area, we have 14.64 square meter. That's the area 2. So we can now compute using end area method. So using end area method, the question letter A. So by end area method, just take the average of area 1 and area 2 and multiply it by the distance between the two stations. So we have station 1 plus 100, station 1 plus 200. So the distance between them is just 20 meters. So your L here is 20 meters. So the computed area are 13 plus 1625. Okay, 13 plus 1625 plus area 2, 14.64 to be divided by 2 times L, which is 20. So the volume for end area is equals to 278.025 cubic meters. That's your answer for letter A. Okay, so letter B, required to determine the corrected volume. So we apply prismoidal correction. So for the prismoidal correction, just identify the C1 and and D1 for the first station, station 1 plus 100. Our C1 there is this one. Okay, so the vertical distance at the center and the total horizontal distance is 10.95 when we add 6.45 and 4.5. When we add 6 and 6.9, that's D2. And we have D1, C2 of 1.2. Okay, here. Apply the formula for the volume for prismoidal correction. So volume for prismoidal correction is L over 12 C1 plus C2 times D1 minus D2. Okay. So 20 is L over 12. That's 1.5. 1 minus 1.2 is 10.95 minus 12.9 equals to volume of prismoidal correction negative 0.975. That's in cubic meters. So the corrected volume is equals to volume of end area subtracted by the volume of prismoidal correction. To apply that, we have 278.025, which is computed earlier, minus negative 0.975. So the corrected volume is equals to 279 cubic meters. Okay, it's 279 cubic meters. Next. Next problem here, we will use the prismoidal formula in determining the volume of excavation. Okay, so I think we already know how to draw the cross section of a roadway using cross sectional notes. So let's draw. Okay, so here's the figure for each cross section on station 25 plus 000 and station 25 plus 050. So make sure that you have complete dimension on each cross section and we will use it in determining the area. Now, for the prismoidal formula, as we recall the formula, uh, that's L over 6 times area 1 plus 4 area mid and area 2 should be added for the volume. So it is required there that we have the area at the middle. So the area at the middle is between station 25000 and station 25050. So that's at station 025. So midway between these two stations, we should draw the corresponding cross section at that midpoint or the midsection. So how can we draw that? So basing on the given dimensions at each endpoint or at each station, so in order for us to have the corresponding figure at midway between these two stations, we shall take the average of these dimensions, such as this one, 1.9 and 1.20 and 2.9 to locate the height at midpoint. Another, we take the average of 7.85 and 9.35, or you can use 2.85 and 4.35. Take the average of that, and that's the corresponding offset from the edge of the roadway on the left side. Same way, 5.7 and 3.45. Take the average of that, and 3.8 and 2.3. Take the average of the two to compute the corresponding height from the roadway. So if we take the average of two stations, this will be your mid section. Okay, so this is the mid section. So we compute that these are the dimensions on the left and on the right by taking the average of those values. Okay, from that we can now compute the area at area 1, or at the area at station 25 plus 000, which is what? Dividing it again into uh, different parts. So let's have a separate drawing. Okay, so for area 1, for the area for the first station, divided into several parts. So I will directly write the solution for the area for each triangle. For the first triangle, we have 1 half, base 5, height 1.9. Second triangle, 1 half, base is 3.2, height is 7.85. Third triangle, 1 half, base is 3.2 again, and height is 8.45. Fourth triangle, 1 half, base is 5, and the height is 2.3. Okay, the area 1 is 36.58 square meter. For area 2 is this figure right here. Okay, so for area 2, we have area 1, 2, 3, and 4. So for the first triangle, the base is 5, height is 2.9. Second triangle, base is 2.6, height is total horizontal distance 9.35. Third triangle, 1 half, 2.6 as the base, height is 10.7. And the fourth, 1 half base is 5, height is 3.8. Okay, area 2 is 42.815 square meter. Okay, so for the midsection, find the area at mid. First triangle here, second, third, fourth. First triangle, 1 half, 5, height 2.4. Second triangle, 1 half, 2.9, height Total horizontal distance here is 8.6. Okay, that's 8.6 plus the third triangle, 1 half, 2.9. Total horizontal distance here, 5 plus 4.575. That's 9.575 plus fourth triangle, base is 5, height is 3.05. Therefore, the area at the middle, when you compute that, is 39.979 square meter. Okay, we're now complete in areas. Area at the middle, area at the first, and on the second station. So we can now apply the volume for rhizmoidal formula. Okay. So volume by rhizmoidal formula. Okay. B is equals to L over 6. Area 1 plus 4, area middle plus area 2. Substitute that. So the L is the distance between the two stations, L1 and L2. That's 50 meters. Okay, 50 meters because station 25 plus 000 to station 25 plus 050. That's the total distance of 50 meters. 6, area 1, 36.58 plus 4, area of the middle, 39.979 plus area of the second, 42.815. Okay, so the volume therefore is 1994.26 cubic meters. That's your final answer. Okay.